Okay, so all these springs, they have the same stiffness constant K. We want to find the stiffness constant of this entire system, and by the way, this is just infinite, so the ladder is infinite, right? They even gave us some notation. Now, how do we solve this? First thing that I see in it is that it's symmetric on left and right, so maybe we can merge this, but yeah, I don't like that. uh, we could just think about each platform. So you know that this force exerted by this upper spring is the same thing as the force, the sum of the forces exerted by these lower springs, right? And because the force is just proportional to the compression, so you can say, okay, well, this has what compression? Delta x, I think. No, this thing has delta x, yes, but what about this guy? So this thing, it goes down by delta x1. So this will be delta x minus delta x1, right? So that will be what the force is proportional to. And that's, in fact, let's do it for any generic oops, what's this, for any general platform. So delta x, uh, let's see, first of all, let's talk about this spring. So this is delta x 1, that's how much down it is, but then it's minus delta x2. So delta x I minus delta x, or maybe I should say I minus 1, because in fact we are talking about this platform, so I minus 1 is better. Minus delta x I, yes, that will be equal to, so it will be equal to the force exerted by this plus that, so just like k times that, but we'll cancel that k off anyway. So for this thing it's just delta x2, so this will be delta xi in this case for any general platform, plus let's talk about this one. So for this guy, it's delta x2 down, but then delta x3 is, so this platform is down by delta x3, so that's why the compression is just delta x2 minus delta x3, so this will be delta x I minus delta x I plus 1. Hey, so we got a recursion, really nice. So this is, yeah, like what this delta x I minus 1 is okay, so plus delta x I plus 1 is equal to 3 delta x I. That's good and all, but how do we, yeah, figure out what the actual, wait, what do we mean by this stiffness constant though? That will, right, so the total compression of this thing, which probably is just f upon delta x, yeah. Because that's how much this combination of platform got down. That should make sense, right? Yeah, so if you compress this upper platform by delta x, you will have some retarding force, and then that retarding force upon delta x, that should be our stiffness constant, I think. So what we actually want to find is what is delta x. So this is, let's call this in delta x 0, okay. So 3 times of that, and then minus 2 times of delta x, what is it, right, delta x 1, because symmetry, right? So that's what we are looking for. Is this recursion enough to find everything? So for delta x 0, what, I mean, there's no delta x minus 1, that makes no sense. We just want, okay, right, this is just going to keep on going, that is, it's not nice. So you have no boundary conditions for this thing, which makes it really hard to do. Yeah, come on, think of it, think of something. Oh yeah, so like this force is okay, fine, how does that even help? I don't think it does. Wait a second. Okay, this force, it's getting partitioned, we can think of it like that. So we can assume that delta x infinity, that will be 0, right? We could say that, because look at this recursion. We have delta x I plus 1 is equal to 3 delta x I minus delta x I minus 1, right? Okay, this is not helping. What I really want to prove is that the force keeps on decreasing as we split this, because look, there's some force provided by this spring, some by this, and some by this, and then this force will get split because some will be from here, some will be from here, and then we keep on going like this. Eventually it will become zero, right? That has to be like that, right? So if, for example, the springs couldn't be compressed, like, okay, that's not correct. Oh, yeah, if these platforms were movable, right? So this spring, no, don't think about it like that, but I really want to think about it like that actually. If these springs were movable, then you would definitely get a diminishing force, and in this case too, same thing is happening. In fact, it's even supported, because this will have an extension, sorry, a compression that is less than what it should have been originally, right? Because more forces from here, less forces from there. So I think it's okay to assume that delta xi plus 1 will be less than delta xi. So yeah, but we actually would like to prove that this thing is less than delta xi, which is the same thing as saying that 2 delta xi is less than delta xi minus 1. Okay, right? Do we have to rely on assumptions, or is this actually provable? I mean, you can definitely say that, okay, look, over here the extension is, so whatever force we have over there, right? That, yeah, so over here the extension is, sorry, the compression is more, over here it's less, right? And from that we can figure out something, right? We can figure out some kind of inequality or something. Makes sense. Okay. But now what? Now what do we do with this thing? What if I just solve this recursion, right? That would be okay to do, I think. We can definitely figure out what these forces F1 and this should be if we solve this, right? Yes, that should make sense. Right, so if this force F1, we set it to be something known, it's not known exactly, but if we just take that thing as the boundary condition, then we can solve for this recursion, and then finally we'll be able to find what F is exactly. So think about it. Oof. Yeah, you'll just have to solve this. So let's do it. Let's solve this recursion. So we'll have the characteristic equation, characteristic polynomial equation, yeah, for that, and that will be 1 plus r squared is equal to 3r. In other words, r squared minus 3r plus 1 is equal to 0. I don't think it has repeated roots, so you don't have to worry about multiplying by right, multiplying by n and all that stuff, so no need for that, right? So over here we will just find the roots. It's going to be square root, so like 3 plus minus square root of b square, so 9 minus 4, it's 5 upon 2. So one of them is 3 plus square root 5 upon 2, and the other one is 3 minus square root 5 upon 2. Multiply this thing by alpha, right? So alpha times this to the power of n minus 1, I think that should do it, and then plus beta times this to the power of n minus 1. So this will be that's a guess only, but still it's something that will satisfy this recursion. And now it's time to figure out what exactly this alpha and beta should be. Okay, so right, this is problematic because the thing is we don't know what's exactly happening at these upper layers. We only have been given what this force F is. Oof. Okay, hey, we know what happens at infinity. So at infinity, so this thing is our delta delta xn, yes. So delta x infinity, that will be alpha 3 plus square root 5 upon 2 to the power of infinity minus 1, and this thing is 3 minus square root 5 upon 2 to the power of infinity minus 1. So you can notice that this thing is only bigger than 1, this thing is less than 1. The only way for that force to approach 0 is if this thing is 0. So from it you can say, okay, alpha should be 0 for this to happen. So this is gone. You can just say delta x n is equal to beta times 3 minus square root 5 upon 2 to the power 5 minus 1. Cool. And oh, geometric progression, huh? Nice. Anyway, what we actually need to find is delta x 0 and all that stuff. So this recursion also work for delta x 0? No, it only works for these platforms. What about this platform? So for this platform you will have, so there's this capital F force on this thing, so that's why it's not in delta x values. Okay, but for this platform, what you say, you will say that okay, delta x 0 plus delta x 2, that will be this thing, is equal to 3 times of delta x 1. Fine. Yeah, so it works for that. But what about this platform, huh? So for that platform, I'll just minimize everything. This is nice, right? At least we got the fact that delta x is in geometric progression. So what was this once again? Beta 3 minus square root 5 upon 2, that's the power of n minus 1. And what do we have? For this platform, you can say f is equal to, so let's call this f upon k. F upon k is equal to delta x plus, so over here what will the compression be? It will be 2 times of delta x minus delta x 1. Makes sense, right? And yeah, so delta x 0 is also a part of the series, but it only starts from this platform. I mean, this recursion only starts from that platform, right? So you can still use this thing, no problem with that. And then of course when you put n is equal to, oh, it should be okay, so let's not go for to the power of n minus 1, let's go to the power of n directly. So this will be awesome. So when you put x is equal to 0 in this thing, you will get beta, right? So delta x is equal to beta. So you can say okay, delta x1 is equal to delta x times this thing 3 minus square root 5 upon 2, and then we'll put that in there. Cool. So this is going to be let's see, 3 delta x minus 2 delta x1, which is, so 3 times of delta, okay, that's already there. So delta x, and then you got 3 minus 2 times of this thing, which is minus 3 plus square root 5, I think. Does that make sense? I think it does. This cancels. She's got square root 5 delta x. Oh yes, we got it, we finally got it. Our delta x, that's just equal to f upon square root 5k. Now we can do it, f upon delta x, which is our k dash, I think, that will be square root 5k. So once again, let's just check what we did, because I always kind of make mistakes all the time. So let's do it. First of all, the recursion. So for the recursion we have, so if this thing is the ith layer, right, then over here you will have one spring like this, right? There's only one spring all of the time. So this is delta x I minus 1, it has that compression, and then over here you have this fixed platform and this moving platform. Right, this is I plus 1 layer, the I plus 1 platform, and this is, so yeah, you can say this is lower than this platform by delta x I plus 1, right? So this thing is delta x I plus 1, and of course this thing will have compression of delta x I. So this will have compression of delta x I minus delta x I plus 1, and from there you can say okay, this plus that is equal to, sorry, this is equal to this plus that. So yes, wait, is this supposed to be 2 times of that, or did I make some mistake? Oh, so I did minus delta x I, oh, of course, this is one of those things. So over here you can see that this platform, yes, it is delta x I plus I minus 1 down, but then yeah, the previous platform, right, that's how it should be, right? So the I minus 1 platform, that is in fact delta x I minus 1 down from what it should be, but then this platform is also down, so this has compression of delta x I minus 1 minus delta x I. That's why we got this thing. Yes, yeah, exactly, all the terms are correct. So this is I plus 1 right there. Wait a second. Oh yeah, it's just one of these, and over here you got this thing. So that's why 2 delta x I minus delta x I plus 1. From there you can say that goes over there, 3 delta x I, and this goes over here, so this thing. So 1 plus r square is equal to 3r. So r square minus 3r plus 1 is equal to 0. That will be the characteristic equation. From that you can figure out what r is, which is 3 plus minus square root of 3 square 9, 9 minus 4, 5. So 3 plus minus square root 5 upon 2, and then do the usual thing that you do to solve recursions. But we figure out that alpha is 0 because the other root was bigger than 1, and at infinity your force must be 0, so the compression must be 0. Then fine, you just have this this expression, and yeah, it works. Looks like it did work this time. Okay, yes, alpha is equal to 0, we can conclude that. And now it's up to me to decide if I want to keep n over there or n minus 1 or whatever I want, because we can just change beta accordingly. So I will just keep n, and that's because n equal to 0 just makes this go away. So you can directly say delta x1 is equal to delta x times all this stuff, and then this thing. So cool. So that's it, our effective spring constant, that will be this stiffness whatever, square root 5 times k. So this is it. I'll see you guys in the next video. And by the way, thanks Sumit Rider for this excellent question. It really is nice. Okay, see you guys in the next video.